All right, well, good afternoon. My name is Chris Regals. I'm with Agro America and presenting this webinar on their behalf. So we'll get started here. And today's topic is active landfill gas collection design with ClosureTurf, which is an engineered final cover system. Some of you may be aware of it, some of you, this may be brand new. To that, this is actually part 4 of a 4-part webinar series. Parts 1 and 2 discuss these topics. Part 3 went into passive venting of landfill gas beneath the geomembrane component of ClosureTurf. If you've missed some of these webinars, we'll do a repeat on them sometime in the future, sometime in 2017. If your firm would like a individual presentation, we'll be happy to do that as well. We do those open mic versus mute all on these just to cut down on background noise that seems to be, this platform seems to be famous for. But anyway, if you would like a firm or an individual presentation for your firm and offices, we'll be happy to do that. Give us a shout and we'll get that set up. So anyway, from part 3, we're going to part 4 today. And this is on active landfill gas collection using the ClosureTurf system. This is a new approach to environmental control. Some of the issues we'll be discussing today are recent permitting revisions in the new source performance standards, the effect on stability venting as well as on this system itself. Landfill gas pressure forces, kind of a repeat from part 3. Except in this case, we're going to talk about letting the landfill do all the work in protecting side slope stability. I'm going to talk about the landfill gas collection layer, side slope collection, top deck select collection, and active area collection without vertical wells.
You're serious. I am serious. And don't call me Shirley.
I'm totally serious because it's been working in other installations in the southeast United States. So this is a system, or the next logical step for this system. A little quick review. System weight of ClosureTurf with the sand, turf, and geomembrane components. It's all about 6 pounds per square foot. Factor of safety for stability purposes here for slope stability slide is found from this equation where this variable here, U sub G, is landfill gas pressure. As you can see, it takes away the resisting force on the top of the equation and hence has to be controlled. Depending on the assumption for the factor of safety, a factor of safety of 1.0 is an imminent failure. Landfill gas pressure is only 0.66 inches of water column. At a factor of safety of 1.5, that's 0.45 inches of water column. So right at static stability conditions, it doesn't take a lot of landfill gas pressure to start causing issues. So the point of this webinar is this beast has to be controlled in larger sites. Now going back to our square 100-acre pyramid-shaped site, aka it doesn't exist. Actually, I do know of a design of a site that looks like this. Quite a bit bigger though. This landfill design, I had 90 extraction wells. I've updated it here to more resemble some form of reality in the form of individual gas wells and lateral subsystems, subsets tied into perimeter and slope headers here. However, this is an old school design.
Walk this way.
old school is completely appropriate for old school landfills, aka unlined landfills. That's not what I'm going to be talking about in this webinar. Current active landfill gas control system design has borrowed technology from the oil and gas industry with the vertical well extraction system. It's absolutely necessary for unlined landfills to control subsurface migration. So I'm probably going to repeat this a couple of times, but I just want to make sure everyone understands I'm not talking about those older legacy landfills in this presentation. This system that I'm going to be describing does not apply to unlined landfills. So I just want to make sure that point comes across. In a completely sealed system like a modern day Subtitle D facility, that vertical well system isn't as applicable as it is to the unlined facilities. Hence, we, that being Agri and Watershed Geosynthetics, are proposing a departure from that current vertical well system, or landfill gas collection and control system, GCCS technology. The ClosureTurf final cover system offers options from that standard GCCS. Here I've replaced drilled wells in our 100-acre pyramid landfill with surficial collection wells and surface collection pathways, be that pipe or geosynthetics, depending on the flow needs. In this situation,
This way.
I'll miss Gene Wilder, but he makes an excellent point here. Sometimes we just get stuck doing things a certain way, and then at some point in time we ask, why are we doing them? So that's our point here in presenting this new concept in landfill gas control. Let's start by talking about the hardware. This is basically the Watershed Geosynthetic surficial well. The active components of that well are this piping here, a 2-inch PVC pipe about 3 foot long, this collection footing or collector foot down here, and that has been up to now secured directly beneath the ClosureTurf system sitting on the cover soil. It can connect to any available wellhead product out there, and that's pretty much it as far as the change in hardware. For beneficial use projects, be those power generation or my favorite CNG fuel conversion, still need to use lateral and subheader and header piping to collect that gas and get it to the beneficial use platform. Back on topic, for stability of critical side slopes, for passive venting, the vent version of this equipment was set on the cover soil surface. Active extraction is a little different. For active extraction, we'll use the first refuse lift as the gas relief layer. Now I'm quoting from this paper down here by Rick Teal. It's available on his website. It used to be available on the archive page for geosynthetics. The geosynthetics archive page, that I think has since gone behind a paywall in recent months. But you can pull a copy of this paper from Rick himself. That first refuse lift is typically about 10 to 15 feet thick, depending on the operator. And it's much like a classic well, except without all that deep drilling. Here I've taken that well system, the pipe and the collection foot down below here, and I've set it down below the cover soil onto the refuse lift. Here I've put gravel around it, and that's to allow any condensate that might get into this area here to drip out and not get sucked up the well itself, and also prevent, like, wads of chewing gum and apple seeds and other small diameter refuse particles from getting into the well system. From our cross-section from part 3, the system will look something like this. First, let's take out the drilled wells and replace with a superficial and base collection system. These are all necessary components, and again, this is not applicable to unlined sites. If this component here is not in place, you got to have some method to control gas migration out of the waste mass into the subsurface soils, where they can cause all kinds of hassles: groundwater contamination, methane gas popping up along the perimeter, and fire dangers and all that kind of thing. So anyway, again, I'm not talking unlined landfills. This is lined landfills, period. Now, one thing to keep in mind as we move forward here, and I'll talk about this in a little later, landfill gas temperature in the superficial system is ambient. And that's much different from the core temperature that's going on inside an active, biologically active landfill, about 140 degrees. Well, before I start getting too nerdy with all this stuff, I should probably sober up and talk about the rules, specifically the new source performance standards. That's NSPS, and it's part of the Code of Federal Regulations, Part 60. For landfills, that's subpart W and now subpart XXX. NSPS still requires active control for landfills at 2.5 million megagrams of waste in place and or cubic meters, but has reduced the non-methane organic compound threshold, emission threshold, down from 50 megagrams per year down to 34 megagrams per year. So a lot of sites, active sites that were not covered under this regulation are now. Specifically those that commenced construction, reconstruction, or modification after July 17th, 2014. Where July 17th came from, I don't know, but any site active today that fits those parameters is going to have to install a system. Now, some might say that NSPS does not allow a GCS like what we're proposing. However, Section 60.762 and a whole bunch of letters and numbers after that has this to say: a passive collection system must be installed with liners on the bottom and all sides in all areas in which gas is to be collected. The liners must be installed as required under 40 CFR Part 258.40, aka Subtitle D. So, if a passive system is good enough for Subtitle D, then this style of active GCS is as well. In the last webinar, I discussed use of superficial vents to avoid dangerous gas pressure buildup underneath the geomembrane when the system goes down, as they tend to do. Revised NSPS has some startup, shutdown, and malfunction language, or SSM event, that could be interpreted as applying to these pressure relief valves, in particular the underlined. That requires that all valves in the collection control system potentially contributing to the venting of gas to the atmosphere be closed within 1 hour of the system crash. Now, the underlined text is what some might claim apply to pressure relief valves. We disagree. And the reason is, the question, are the pressure relief valves part of the gas mover collection and control system? No, they only function in the absence of active control. That's their purpose. If there's no active control for an extended length of time, you need to relieve that pressure on the final cover side slopes in particular, or the side slope stability. So if you don't, these are what are technically called very expensive owies. No one wants to get this phone call that something like this has happened at one of their sites. Final cover failures due to gas pressure. Well, we in Agri and Watershed Geosynthetics, we have a solution that stabilizes the slopes and is regulatory compliant. As the waste mass decays, LFG pressure grows from the interior to the base and top surface. So if we let the landfill do all the work, as with a passive system, the active controls within a ClosureTurf GCCS, that'll capture that gas as it approaches the surface collection components, all our superficial wells, and in some cases, some might require some piping, particularly along the side slopes. That's a site-specific issue. Also included is the LCRS. So we use those two, the bottom and the top, to route gas to the control device using a typical header, subheader piping system that people are probably already familiar with, in particular for those sites with methane beneficial use. So that's our proposed ClosureTurf based GCCS. How does it work? Well, per Rick Teal's paper, we're using the last refuse lift as the gas relief layer from this equation here and in this scenario. So here's all the variables in that equation. So we've got UG sub max, which is the gas pressure at the wellhead, basically, developing from a pressure of 0 here, a distance L from this well, which is basically the half well spacing from well to well here. D is the gas relief layer thickness, and that's what I'm calling the first, or that top refuse lift, so 10 to 15 feet. And then X is distance along here from pressure at 0 towards the collecting well head. And then we have gas flux per unit area, gas unit weight, and refuse gas permeability. All these variables have published values except for gas flux. That's site dependent. However, I can estimate that gas flux using some published values for gas generation rates that I presented in part 3 that are dependent on refuse age. Those generation rates were 6, 14, and 17.1 milliliters per kilogram of waste per day. So within, say, a 100-foot tall landfill above the surrounding grade, how does gas move within the waste mass? Well, leachate recirculation research indicates refuse horizontal permeability can be 10 to 35 times greater than vertical, and that's from this paper down here on leachate recirculation, which does not have an active link right here. I'll find that for you if you want to try to pull that paper down. It's from ASCE. I think it's behind a paywall, so you'll have to purchase it. So I'll assume that vertical flow is a 25th that of horizontal flow as an average. So gas flow using those generation rates would be something like this. Most of it going towards the side slope collectors, and then some rising up to the top. Now, using a well bench spacing of 200 feet and this horizontal reach into the landfill itself, I'm going to get these type of gas flows at the upper, the middle, and the lower bench. So 14, 18.4, and 11.4 CFM flowing to a collector point here, say here, here, and here. So now we know some gas flow rates the superficial wells will have to accommodate. For the mid-bench well, Q of 18.4 CFM, we'll figure out that the gas flux per unit area is that flow divided by the well spacing, 200 feet, by the slope length. So its value inside the equation here is basically 8.8 cubic feet per minute per square foot. That's a goodly amount of flow. And a gas density of 0.08 pounds per cubic feet with a gas permeability of 1 times 10 to the minus 3 centimeters per second, or its conversion into English units. Gas lift 15 feet, length between the wells 100 feet, or half distance between the wells 100 feet, and then X equal L at the well. And we calculate this pressure at the wellhead, one of these wellheads, say right here, 2.3 inches of water column. So with a pretty mild vacuum application, a superficial well can have a radius of influence of 100 feet. So are vertical drilled wells even needed? In a completely sealed system, we're saying no, they're not. Also, this ClosureTurf based GCCS is adaptable depending on horizontal versus vertical gas flow directions, such as in the refuse cover practices of a site. We can adjust the superficial collection system to adapt to specific landfill conditions. What's that mean? Well, say if we strip landing pad soil cover before placing new refuse lifts, as a lot of landfill operating companies do already, that allows refuse lift-to-lift contact. So landfill gas movement in the interior may more closely resemble this. And here I presume landfill gas will move up versus down, since the refuse lifts are less dense towards the top. Now bench wells will see these kind of flows under that kind of regime. So dropping down from the middle bench there, dropping down from 18.4 to 11.4 CFM. Not a astronomical difference, but significant. And that would require an applied vacuum at a mid-slope well of 1.4 inches of water column. So still pretty mild vacuum application to get all these wells to do their job. What about the top deck? At some distance from the side slope, all the gas will be migrating to the surface. Well, how much? Well, here I'm going to assume the baseliner lifts, or those lifts below the surrounding grade, will flow into the LCRS. More on that in a bit. But using our generation rates, we're going to see this type of gas moving up towards the final cover system. Somewhere in the interior, a pressure boundary will develop where the gas pressure generation here versus here are going to be equal. So this landfill gas mass here is not going to move towards the side slope. It's going to move towards the top in this fashion, top or bottom. Like I said, a little bit may head down towards the LCRS, but the assumption in this webinar anyway is a lot of it's going to head towards the top, and it's going to have to be controlled. Spacing each well to cover an acre, well, that implies volume of 100-foot deep waste mass. To be controlled by each well is simply, well, this, about 161 cubic yards and some change. But you got to remember the lifts are of different unit weights and gas generation rates. So we're going to have to calculate that for each, the upper, the middle, and the lower levels of waste lifts, as I've done here. So total gas flux that I'm calculating here is 1.14 times 10 to the minus 5 cubic feet per second per square foot. So now that we know that, I can calculate the required vacuum at the wellhead in the gas relief layer. This 15-foot thick layer, gas rising vertically up towards it, and then feeling the vacuum application from the wellhead here moves horizontally towards the wellhead. And calculations here indicate the pressure, minimum pressure that this well would have to apply to this mass would be about 2 inches water column and would move about 30 cubic feet per minute. That's not a monster flow, but my hypothetical landfill, it's not a monster site either. The low applied vacuum, that allows for a lot of room for application at larger sites. So we're confident that this will work just about anywhere. Anyway, if I'm letting the landfill process do all the work and the trash serve as a flow conduit, I don't have to apply huge vacuums with a ClosureTurf based GCCS. I mean, you can always increase the density of wells if you want to operate at a lower vacuum pressure, or you want to make sure that you have appropriate coverage. These vertical well placements or superficial well placements here are very cheap compared to vertical wells, which are about $100 a foot. So 100-foot deep well, you could drop $10,000 on that. What about baseliner collection? Well, that depends on the material in the LCRS. For this specific module here, its area is about 8.1 acres or 352,000 square feet. If I place a cleanout pipe above the sump into the trough here, the collection trough of this baseliner, I can use the LCRS material as a blanket collection system. For this model, I already assumed Topdeck landing pad soil is being recovered, and there is waste-to-waste contact. Only daily cell slope soil remains, or in some cases that may be stripped as well. So the refuse cover ratio is about 5 to 6 to 1. That's pretty dang thin, which implies the baseliner only need be excavated an average of 15 feet below surrounding grade to provide all that cover, to provide the cover soil. That implies a waste volume within that module of about 195,600 cubic yards at 20 feet deep at its deepest point, all generating gas to be collected at the LCRS sump cleanup. With a refuse density of 1,600 pounds per cubic feet and generation rate of 6 milliliters of gas per cubic kilogram of waste per day, landfill gas flow from this LCRS is 21 CFM. Now the question is, how much delta P does that require to drive this system? Vacuum distribution across an LCRS will have a trapezoidal shape as the pressure drops deeper into the module like this. This is the, say, the clean out for the LCRS here, and here it is at its far end. Gas flow within the LCRS media, in this case I'm talking about gravel, it can be geocomposite as well, it'll follow Darcy's law, taking this form here. With K, the permeability of the gravel drainage media, and expanded into this form here. Now this This reference here is available at the ASCE. It's behind a paywall, so you got to purchase it, but that's what this part of the presentation here is based on. This presentation was made back in 1997, so this is 20-year-old technology basically. The velocity V can also be determined using orifice flow calcs into the perforations of the LCRS collection pipe. So the flow through the gravel is going to be restricted by the orifice conditions of the pipe perforations, or velocity will take one of these two forms. Now here I've dropped Z out of the equation, out of this equation here, because I'm assuming it's negligible for gas. Now, since K describes hydraulic flow, we got to convert it to intrinsic permeability, or the intrinsic permeability of the gravel itself, regardless of the fluid flowing through it. So, converting to intrinsic, simply the hydraulic or permeability multiplied by the viscosity divided by the unit weight of the fluid. So now that equation takes this shape. I rearrange and integrate, and I've got an equation that looks like this. Now if I go ahead and go through with the integration, it takes this form. So now knowing all these other variables here, I can solve for pressure. Now here are the values here of all these different variables, with pressure being the unknown. Solving for P and then converting from pascals, this is a metric equation format shown here. Converting from pascals into inches of water column, I get a applied pressure requirement of 7.6 inches of water column, so much higher than the superficial wells. This is the applied pressure at the far distal end of the pipe, so we still got to figure out pressure drop across the pipe itself to know what the required applied pressure at the clean out riser is. So go through Darcy-Weisbach and solve for that. We've got turbulent flow within that pipe with a Reynolds number of 6,500 basically. So calculate the friction factor, and well, pressure drop's only about 0.05 of an inch of water column. So applied vacuum at the LCRS wellhead is 7.65 inches, or 8 inches rounding up. Now one thing I did assume is that they're using Darcy's law, is there's laminar flow in the LCRS gravel. Let's see if that's the case. So we'll go through the Reynolds number calculation here, and it's laminar, it's way laminar. Now what about geocomposite? Well, geocomposite transmissivity is only equivalent to a gravel LCRS transmissivity-wise in confined conditions, aka they are both saturated. And this is based on this paper at, yes, Geosynthetic Society.org. Sorry, this link is probably broken because I think all this stuff is behind a paywall now. You'll have to search for it on their website and likely have to pay a nominal fee for these papers that I'm referencing. Anyway, both would have to be saturated. Gravel LCRS is never fully saturated. If it was, that would mean it's a failed LCRS, because you can't have more than 30 centimeters of fluid depth at the sump. So this field out here cannot be saturated in a gravel system. It may be with a geosynthetic system or a geocomposite LCRS. Reynolds number for landfill gas flow in a geocomposite, it's still laminar, but the required vacuum, it's so high that all the gas will have migrated to the landfill top before it gets down into this geocomposite LCRS. Still, it's advisable to apply a vacuum to a geocomposite LCRS to prevent gas migration across the liner into the subgrade soils through flaws like pinholes, tears, shovel smiles, those never happen, etc. So now that we can control landfill gas within a sealed mass, now what? Well, where's it going? Control devices, power plant, flare. How do I get it there? For a site with no valuable energy content, that's a flare. If it still falls within NSPS's target range. How that's typically been a central enclosed ground flare. Still requires piping and a vacuum supply blower servicing the entire facility. That is a problem here in the People's Republic of California. Our AB 32 regulations require active landfill gas control on sites with a heat capacity greater than 3 million BTUs per hour. There's not a lot of flares out there at that heat rating and turn down ratios anyway. There are individual flares, solar spark comes to mind, that could be used at specific surficial and LCRS wellheads. But again, here in California, air permitting for these devices is kind of dicey because you can't necessarily do source control testing on them. Power plant, those come with their own blower systems, so not an issue. Conveyance, well, when I said earlier, the usual header pipe, subheaders, well laterals, and condensate sumps. Oh yeah, about that condensate. Extracting hot and saturated gas from the center of the landfill up to the surface in a matter of seconds produces buku condensate in the pipe, particularly in the colder night. So all that condensate has to be controlled too under the current standard GCCS designs. Now, if we allow the landfill to do the work, means the gas approaching a surficial, a ClosureTurf, or a ClosureTurf GCCS will cool slowly inside the waste mass, allowing most of the entrained moisture to drop out before it reaches the surficial GCCS. This has been our observations at installed systems in the southeastern United States. There's not a lot of condensate to deal with this style of gas collection. If LFG is conveyed to a collection header, like with this standard system depicted here, in a ClosureTurf GCCS, condensate would be a very minor issue compared to the standard system. Could be managed using re-injection drip legs or via vacuum taps on the LCRS cleanouts and at the header pipe low points versus collection sumps and pneumatically controlled pump stations. So much like I pointed out here, low points of the collection header would have a drip leg or drop leg down to the LCRS cleanout tap here and say here to get rid of any condensate that might collect in this pipe. Basically, we here at Agri and Watershed Geosynthetics, in this proposed design, we've strived to have minimal moving parts. Those moving parts mean maintenance dollars. So we're trying to let the landfill do as much work as possible and us just providing direction on where we want that gas to go. Now the collection pipe network is pretty standard fare, calculation-wise. Except in those typical systems, you usually leave like a 10-inch residual vacuum in the network to apply to the vertical wells. Now, as we saw previously, the superficial wells need up to 2 inches of water column. So let's say less than 5 inches of residual vacuum in the network to apply to those superficial wells. The pressure drop calculations across the piping network are typically conducted with a low pressure Mueller equation, which takes on this form in English units. The LP Mueller is in reasonable agreement with Darcy-Weisbach and has the bonus feature is it doesn't require constant iterative solutions of the Colebrook equation to determine the friction factor F in the Darcy-Weisbach. You don't see F anywhere in this equation here. Hence, it's easily pluggable into Excel, such as I've done here for the north perimeter header of that hypothetical landfill. So I've got the low pressure Mueller equation plugged into this link here. Here's flow Q, the length of pipe L, cumulative flow that might move along that will move along in the header. Gas density factor here, 0.87, constant always, and then pipe diameters, nominal size, and then actual inside dimensions, and then calculates the delta P in inches of water column here. So sum all that up, I got a total pressure drop of almost 23 inches of water column. One rule of thumb is always keep the pipe velocity less than 1,200 feet per minute. This allows you to do that by increasing the pipe diameter, and this allows condensate to drop out and also keeps delta P reasonably low. One thing in this table here is you'll notice that the LCRS sumps generate a lot of delta P, or require a lot of delta P to get that pressure to apply across all the gravel. So what you might want to think is putting the LCRS sumps on a separate header, and then you can drop the gas collection pipe network down to 15 inches of water column, which applied in parallel would still apply to the you could still apply the required pressure at the LCRS sumps themselves down to 15 inches of water column. Or we're going to make that pressure drop similar to that on the southern header, which here is about 13, 14 inches of water column. Oh yeah, I should have increased pipe size here, but corrections like this are easy to do, hence this is a really nifty design tool in determining what your pipe network sizes need to be, so that you can get this gas, all this gas moving to the control source or beneficial use. Now, what about in active areas? Active area, active landfill gas control. That's emissions control, not so much gas collection for beneficial use. You just got to prevent superficial emissions from occurring in your active areas, either active landfilling areas or those that have been active, say, for 180 days or more. One thing about these controls is they're not intended to be permanent in this presentation anyway. Here what we're talking about using is an inverted strip, say 5 feet wide or wider or tighter spacing or what have you, inverted strip of super grip net or drain liner, and use that as a horizontal collector along slope toes directly on the waste. And it would take on this configuration here. This is a piece of super grip net anyway, turned upside down, so the studs are sitting right on top of the garbage. Grips are up here, and gas is flowing in this void space created by the studs. We think it'll work. We need a demonstration site volunteer. So if you know somebody that would like to give this a whirl, get in contact with us and we'll get something set up. And of course, if those don't work, we can always revert back to the old standby of a drilled well, which can have anyway, short lifespans in active areas because of this fella right here. So anyway, it's an option. If you got more questions on this or know of a site that might want to give it a try, give us a shout. There'll be a list of names at the end of the presentation that you can contact. So anyway, conclusion. The ClosureTurf final cover system can be adapted now as an active GCCS system. It is an active GCCS system in several installations in the southeastern United States. Talked to both either us or Watershed Geosynthetics about this. It does work. Hence, the components are currently available, minimal moving parts, lower vacuum requirements, and no well drilling. Also, there's more to come, more ideas that we're still vetting that weren't ready for prime time in this presentation anyway. But bottom line conclusion we're coming to is ClosureTurf is evolving into what I'm going to call an integrated environmental control system. That includes final cover, landfill gas control, stormwater conveyance and pollution control, among others. So questions, contact any one of these three, myself right here, Chris at cregals@agroamerica.com, or Nathan Ivy, N-I-V at agroamerican.com, or Delaney Lewis, D. Lewis at watershedgeo.com. So Delaney's the Vice President of Operations for Watershed Geosynthetics, and he's the prime mover in the landfill gas collection features of ClosureTurf. For those of you needing PDH credit, those are available by the state shown here, where I've shown required hours per renewal period in years. These states allow PDH credit via webinar. If you're tuning in from Oklahoma or Louisiana or Florida or North Carolina or New York, sorry, I can't offer you PDH credit. Those states have pre-qualifications for presenters such as Agro or Watershed Geosynthetics that we haven't attempted to get. So anyway, if you're in any of these other states here that require it, give us a call and we'll get you a PDH cert. So anyway, that's the presentation. Again, if you've got questions, give any one of us here a holler and we'll get it figured out for you. In the meantime, if anyone wants to type in a question in the chat box, we've still got about 10 minutes before lunch hour is up and everyone's got to go back to work. I'll hang here for a few minutes if anyone's got an immediate question. Otherwise, we'll hear from you later. All right. Well, seeing no questions, I'll sign off here, and we'll see you next time. And keep an ear out for presentations on our website, or talk to your local representative, agri representative, and they'll keep you informed as to what we're going to be doing into the future. Next series that we're intending on putting on, I'm going to call Geosynthetics 101, where we're basically kind of walking you through the basics of geosynthetics design. That's going to be aimed more at entry-level staff employees, engineers that are out of college or a few years out of college that may not have been exposed too much to geosynthetics during their coursework. And project managers and engineers would love for them to get up to speed on using this stuff. It's not all that complicated. You just need to do a little bit of work on it. So anyway, not seeing any questions. We'll see you next time, and thanks for tuning in.